Hello, Krisha. Ah, Chris is chilling on the beach today. Oh, no, that's too bad. I wouldn't mind teaching from the beach. In fact, I actually did for the first 2 weeks of coronavirus. We left China. My family went to Vietnam and stayed at a super cheap hotel on the beach. And I literally taught from either the beach or very close to it for the first 2 weeks of the whole coronavirus thing before we figured out it wasn't going to last 2 weeks. It was going to be much, much longer than that. Wow. Akrit's got somebody watching over his shoulder there. Oh. Is he going to show up?
I will just leave this here the whole class. Don't mind.
Bring it on. Bring it on. Okay. Thanks for hanging out. Sorry I'm a couple of minutes late. Oh, wait. How is he there? He's in both places at once. How are you doing that, Ram?
What? Wait, I don't.
You were just at Akrit's house.
Oh, yeah, he set it as a background. He always does that.
He just misses you so much. All right. All right. Okay. So yeah, thanks for hanging out for a few minutes. I'm hoping that everybody else will kind of trickle in as they figure out that I'm here now. I appreciate you being patient as I transfer here to school so that I can try to teach from here. All right. I think before anything else, do you have any questions of things that you read about or things that you've been thinking about, or questions about somebody's demo or a demo that you saw as you were trying to come up with your own? Any questions before we get moving?
Yeah, what demo are you talking about?
Your homework.
We had examples 5, 6, and 7.
Oh, just kidding.
The notes.
Yeah,
we thought you were a bit confused because you told us to check the
I
fourth
was,
grade, and
yeah, I was
were
totally
a bit scared.
No, yeah, no, now that I'm looking at your faces, I'm realizing that none of you made demos, which would make sense because that was for year one. Okay. Sorry. No, I'm glad that you had a few minutes of break then before class started, doing nothing productive, hopefully. Okay. Yeah, I apologize. I was thinking about them. I actually, I created a quiz for them a little while ago, and I thought I was being so fun and sneaky putting their names into the quiz. And then after I wrote the whole quiz, I realized that I put your names in there instead of theirs. So you're forever immortalized in a physics 1 quiz. But anyway, yeah, I told you guys at the beginning of the year, I don't know what's going on half the time. So I hope this is a good demonstration of that. And yet I can still live a happy life and be mildly successful. And yeah, so it's a good demonstration of that, if nothing else. All right. Yes, I apologize if that led to a little bit of freaking out for the first 5 minutes. Nope, that's my fault. Okay. Are there any other questions relevant to what we've been talking about recently?
I still don't really understand the purpose of using root mean squared to find the velocity.
Without going super deeply into the mathematics, there's not really a good way of explaining it. The best way that I can say is that we have stated that for an ideal gas, the kinetic energy is proportional to the internal kinetic energy, or the internal energy of the object, right? We've said it's proportional to the temperature, right? That works for an ideal gas. And in testing, kinetic energy is related to the speed, the velocity, right? The 1/2 mv squared. And so when they've looked at the particles, the easiest way to say it is that when they look at the particles, taking just the arithmetic mean, just adding everything together and dividing by how many there are, that has not given them the correct kinetic energy, right? It gives them a kinetic energy that is not proportional to the like we want it to be theoretically. They have found that it's actually the geometric mean, and it's because of kinetic energy being 1/2 mv squared. Because the velocity is being squared there, we have to use what's called the geometric mean, not the arithmetic mean, or something similar to that. It's not even geometric mean, it's the root mean squared, which is averaging the squares and then square rooting it. The math works out that way. Like I say, the time that it would take to go into all the formulas and the calculus and other things necessary to really prove that are not really worth our time. Okay, but yeah, unfortunately, there's not really a better way to explain it other than that noting in order for that relationship to be true, we need to use the RMS velocity, not the regular average velocity. It doesn't work mathematically. And you can't use the most probable one either, right? We talked about the curve and how you have a most probable velocity. That one doesn't work either. The only one that actually works out to be proportional when you do all the deeper physics and math and stuff ends up being the RMS because of the mathematics involved there. Yeah.
So basically, the context that we'd use it in is that if we're using kinetic energy in a calculation, then you'd use RMS velocity, right?
That's right. You should be using the RMS, which is the average speed. It's just it's a different type of average, right? In your mathematical lives, you've always considered the average just to be add things together and divide by how many there are. But that's the arithmetic average. There's also a geometric average where you multiply everything and then divide. There's also the root mean squared average, which is a different type of mean. Just like you have mean, median, mode, which are all central tendencies, there are actually different types of means. So, and they can be used in different scenarios to find a specific average, whatever you want the average to be representing. And in this case, we need it to connect to that kinetic energy, which is 1/2 mv squared. Yeah. Okay. Other questions?
So when I was doing the homework, I got kind of stuck on example 7, part C. I was wondering if you could.
In part B, you found the kinetic energy, right?
Yeah.
Okay, so that goes hand in hand with the discussion I was just having with Akrit, that kinetic energy equals 1/2 mv squared. So if you know the kinetic energy of a particle, you can use its molar mass, right? Which you can look those up. For oxygen, it's O2, so that would be 32 grams per mole, or 32 AMU for one molecule. And nitrogen would be 28 because you got 2 nitrogen molecules there. So you put that in for the mass, and then that should allow you to solve for the velocity in 1/2 mv squared.
Okay, yeah, that explains it.
Yeah, because that velocity that we're talking about there is the RMS velocity. And so that's how we would go about that.
Wait, what mass do you use for that? Because
The mass of a molecule.
because of okay, that's a very small number.
It is a very small number.
How do you find that? You find it by taking the molar mass and doing something with Avogadro's number, dividing it by Avogadro's number.
Yeah.
Okay, I think that's what I did wrong because I got an absurdly large number and couldn't figure out why. And I think I forgot to divide it by Avogadro's number.
Yeah, and actually it looks like I'm rereading the question. It looks like you found the average translational kinetic energy of a molecule of oxygen in part A. B is a whole mole. So you could use either of those numbers, just make sure that you use the correct mass, right? Because you're talking about it's a really small number. Well, the actual energy of a single molecule is a small number, right? That was that first part, which was 6.21 times 10 to the negative 21. So you do have a very small energy there that you're putting into your 1/2 mv squared. And so then you'll have a small mass, you'll divide the small energy by the small mass, and then you should be able to get a reasonable velocity there.
So the small mass would be the molar mass over the Avogadro's number.
Right, because if you're using, well, it depends on which energy you're using, but if you're using the energy of one molecule, which is what you found in part A, then yes, you're going to use the molar mass divided by Avogadro's number so that you have the mass of one molecule.
Okay, thank you.
Yeah, and remember to put it in kilograms so that we're in SI. The molar mass is usually given in grams, and so you may have to turn that into kilograms first to get the right answer in the end.
I think that might be what I did wrong because I used the mass from part B, which would mean I should have used the not divided the mass by Avogadro's number.
Right.
But I did it in grams. Which is probably why that's messed up.
Yeah, so kilograms. Yeah.
Yeah,
that may
makes
be it.
sense now.
All right, anything else? Okay, awesome. One thing I want to mention just before we start talking about something a little bit different is, not just a little bit, I mean, connecting to something else, is the fact that for an ideal gas, a lot of these things work out nicely because in an ideal gas, we're assuming that there are no interactions. We're assuming that there's no chemical energy within the molecules. We're just looking at, we're saying that the internal energy and the thermal energy are equal inside an ideal gas, right? It's actually that question that you guys are asking about with oxygen and nitrogen is actually a really, really bad example, because if you have two oxygen molecules, they actually do have some internal chemical energy, and oxygen is not a very good ideal gas. Neither is nitrogen for that reason. So, I mean, it's there and we can make the calculations and we can get some roundabout answers, but in reality, it doesn't work out too well, because if you have more than one atom, it doesn't really end up being a very good ideal gas. So keep in mind, for an ideal gas, because we're ignoring all that other internal stuff, we're saying that all of the internal energy is thermal energy. If you take, I always make sure to mention this, because if you do take further classes in thermodynamics or even a deeper physics class, they'll talk about that and they'll say, well, for a diatomic molecule, you have a different formula. For water, which has more than two atoms, you have to use this other formula. So there are different formulas as soon as you go away from your monatomic atoms, which is what we're usually considering for an ideal gas. The assumptions are better for monatomic. Okay. Awesome. Let me then share this with you. We're not going to take too much time on this. However, I think this is interesting to look at and consider with respect to some of the things that we've been talking about. So here we go. All right. So, you know, we're actually going to go to water here just because water is cool. All right. So right now you can see that we're at 146 Kelvin. You can see the temperature right there. I've got a really snazzy bucket here. I wish I had one of these in the classroom. I can either flip the lever up and it heats up the molecules, or I can flip the lever down and it cools off the molecules. Wouldn't that be a neat thing for demos? Just flick the switch and it just changes it. Anyway, so you can tell that right now we're at 154 Kelvin, which is well below the freezing point. What do you see the molecules doing?
They're vibrating.
They're vibrating, right? But for the most part, my block of ice is staying basically the same shape, right? There's a little bit of variation in the individual molecules, but for the most part, it's just vibration. All right, let's heat it up a little bit. Let's get it up to the point where it's going to melt. There we go. We start to get some melting. Okay, so now we've definitely melted. We're past that 273. And you'll notice that, what do you see about the molecules at this point?
They're closer together.
They're closer together, right? Which is something that we see with water specifically, right? This isn't the case for all molecules. It is for water because of the hydrogen bonds. When you're in liquid form, the hydrogen bonds actually allow the liquid to contract. Water is, you know, we often look at water and see, oh, water expands when it freezes. That's not normal for normal materials. And so we want to be careful not to extend that idea to everything. It does happen with water because of the way that the hydrogen bonds work. But yeah, so it's definitely decreased in volume a little bit, like we see when it melts. What else?
They're moving more freely.
Okay, they're moving a little more freely, right? Being an animation, it's not perfect. They're still not quite slopping down to the bottom. I'm going to add a little bit more temperature in there. Okay. You can see different types of motion going on there, right? Some are just kind of vibrating back and forth. Some are spinning around, right? Different types of energies going on. Oh, what just happened over here on the left-hand side?
Just collided with the wall.
Yeah, but it's not attached to all the others.
It's
How did that happen? I'm going to pause. Sorry?
It evaporated into a gas.
Yeah, it evaporated, but we're at 319 Kelvin. That's well below the boiling point. How is that even possible?
Oh, that's just like an average, I guess. If you were to look at the curve, there's some molecules that are at a higher temperature themselves than the average temperature.
Yeah. Remember, we were talking about this curve thing last class, right? And we said that the temperature is proportional to the average kinetic energy. So that's these guys right here. But there's still a finite probability that I'm going to have some guys that are out here on the end that have enough energy to overcome the bonds that are holding that liquid together. Okay. Now I want you to think about this. I'm going to send you into a breakout room because I really want you to think about what's going to happen here. What happens to the temperature of the water, the bulk of the water, when one of these molecules leaves? Okay, when we have, and you mentioned it was evaporation, which is probably the correct term for this here because we're not at a boiling temperature. So when molecules evaporate, what happens to the temperature of the liquid? Okay, so I'm gonna just send you out in some random breakout rooms. You'll have 60 seconds. Oh, they've changed this. I don't know what to think about this. Okay. Okay. You got 1 minute? Go for it. What's happening to the temperature of the water? All right. What'd you guys come up with? Adit, what'd you guys come up with, dude?
We said basically it would decrease because the average, like, since that one molecule is like a higher temperature because it's evaporating much quickly, so the average temperature would basically decrease since that higher temperature was going up. That's, I guess that's in simple terms, that's what we thought.
Okay. Any other thoughts? Yeah, Dory.
I also thought it was decreasing, but I had a different explanation for it. I know that evaporation is an endothermic process, so it has to take some of the energy of the system. So just like if you like sweat, that like cools off your body. So, and that's just the sweat evaporating. So I would say that this would also cool the remaining water.
Okay. Awesome. Awesome. So yeah, what Dory's mentioning is a very macroscopic way of looking at it. And then what Adit was talking about is the reason why it's endothermic, right? That's why it actually works, because physically what's happening is you're taking off the highest energy particles. And if you take off the highest energy particles, what happens to the rest of it? On average, it's going to have a lower average than it did before, because you're taking away the high energy particles that are causing it to skew in that direction. Okay, so yeah, that's great. I'm glad that we had a chance to kind of talk about this and make a connection to something that maybe you already learned or knew from a different course or from your reading. So that's great. Really, that's what we want to be able to do here, is take these general ideas that we've learned before and be able to dig in and say, okay, why are these things happening? Okay, great. I think that's all I wanted to get from there. Let's see. Okay, so yeah, as I mentioned earlier, I was just getting up to school as I started this today, so I didn't get to set up my hot plate demo. It's not super important because it's not technically in the curriculum anymore. I do like to mention it just because it's using these ideas and really digging into it to the things that we've been talking about. And conceptually, this can show up. Okay, so I want to show you what I would have done is I would have taken a beaker of ice, and maybe I'll try this next time if I can get up to school a little bit earlier and show you when you have a beaker of ice, the ice is going to be somewhere below zero, right? It's been in your freezer, which is often -4 or -6 or maybe -10 if you got a really good freezer. So your ice is at freezing. when you bring it into the room or put it on a hot plate, it starts to warm up, right? Now, as it starts to warm up, the ice starts to warm until it gets to 0, okay? Now, when you get to 0, what you see, if you keep it mixing and you keep all of that ice the same temperature, it warms up to 0 degrees Celsius. And then when it gets there, you actually see the temperature pause for a while. The temperature stays at 0 degrees Celsius for a significant amount of time, during which time the ice is melting. The ice is at 0 degrees Celsius and the water is at 0 degrees Celsius. It's all at 0 degrees Celsius. Okay. Why then, where is the energy going? Right? If it's not, we're letting the energy of the room or the energy of the hot plate go into the ice. Where is the energy going if it's not changing the temperature for this time period? What do you think, Sophia?
Yeah, so when it reaches the freezing point, then the energy stops going towards like a change in the temperature, I guess, and it goes towards like breaking the intermolecular forces, so that it goes from being solid to liquid.
Yeah, that's exactly right. Instead of the energy going into changing the kinetic energy of the molecules, it actually goes into breaking those bonds. Bless you, Dory. Bless you again. So yeah, it goes into breaking those bonds so that they're no longer fixed in place. And so that's what's happening here. And we call this a latent heat. Okay. Okay, a latent heat, because this is where energy is still going into our substance, but it's not changing temperature, it's changing its phase. And the phase change requires energy because, as Sophia mentioned, you're breaking those bonds. You're taking those molecules that are fixed, and technically we're not breaking them yet, we're weakening them so that the molecules are free to move around. You saw in the animation, actually I still have that animation up, don't I? Let me stop that. We don't need to look at that anymore. All right, so we still have, you know, it's a liquid and the molecules are still stuck together. They're not free to go anywhere. So we haven't broken the bonds, but we have weakened them. All right, we see the same thing after everything is melted and it heats up to 100 degrees Celsius. At this point, again, we see a flat line. Okay, where the temperature of the water stays at 100 degrees. Okay, and the temperature stays at 100 degrees until the water has all boiled off. Okay, and again, no temperature change, yet we're still adding energy into the water. Aisha, where do you think that energy is going? If it's not going into causing it to have more kinetic energy, where would that energy be going?
I feel like between the actual like gas and liquid, it's just between the two distributing until it gets to a certain point where it all has to change into gas, and that's when the kinetic energy actually starts to increase.
Okay, good. As long as we keep it constantly mixing, right? That will be the case. Yeah, all of that energy will go into the transition from the liquid to the gas. And physically what it's happening is in the same scenario as when we go from the solid to the liquid where it's weakening the bonds. In this situation, when it becomes a gas, it's completely breaking those bonds, allowing those molecules now to no longer be attached, to go wherever they want, right? And so that's what's happening in that phase. Again, this is a latent heat. We're not going to talk about latent heat of vaporization, latent heat of any of those other things, but I wanted you at least to make some connections and recognize that, you know, I always tell my wife when she's boiling something on the stove, a lot of people think that if you turn up the heat, whatever you're boiling is going to cook faster. It doesn't. turning up the heat is not going to cause whatever you're cooking to heat faster. Once it's at boiling, doesn't cause it to heat any fat, to cook any faster. Why is that? Yeah, Aisha?
Because you're at that point, you're not gonna make the water any hotter. You're just gonna make it evaporate.
Exactly right. It doesn't matter how long your water's sitting on the stove, as long as it's boiling, it's still at 100 degrees. Still at 100 degrees. And in fact, any extra energy you're putting in is actually leaving in the form of steam, right? It's actually taking more energy away. And so it doesn't do you any good to jam that thing up to maximum if you can put it on low and still be boiling. Okay, now there is a difference between boiling and simmering, which is why some recipes talk about that. One is actually at that boiling state and one is very, very close. But think about that. Next time you're boiling something on the stove, do you really need to jack it up all the way, or can you turn it down a little bit, save a little gas, save a little electricity? All right. Okay. Any questions about any of that before we kind of move into something different? Hope you've had more than 3, but yeah, we'll take that one. We learned about gas last time, right, Isaac? When to get your gas. That was a couple of times ago, maybe 2 or 3 times ago, right? Ah, I see what you did there. All right. Okay. Questions? Okay, then we're gonna move on. Have any of you guys ever seen the story, the movie A Christmas Story? No? Sophia, you're smiling. Have you seen it? Or are you just smiling because you know I'm going to show you a clip from a movie?
No, I'm not sure.
Oh, David's seen it. David knows what I'm talking about. All right. I am going to actually share a clip from this movie because it has something to do with what we're about to talk about. And it's just kind of funny, which is okay to do sometime. Okay. I'm not going to do the full 3 minutes. And I do need to make sure to share my screen, right? And I also need to share the video. So let's go share screen, Christmas Story, the Triple Dog Dare, and let's see. And share computer sound. All right, here we go. Let me know right away if you can't hear anything or if you can't see it, but I think we should be good to go. The old movie.
You're full of beans and so's your old man. Oh, yeah. Yeah! Says who? Says me. Oh, yeah. Yeah! I double dare you.
The exact exchange and nuance of phrase in this ritual is very important.
Huh, are you kidding? Stick my tongue to that stupid pole, that's dumb. That's because you know it'll stick. You're full of it. Oh, yeah? Yeah! Well, I double dog dare you.
Now it was serious. A double dog dare. What else was left but a triple dare you? And finally, the coup de grace of all dares, the sinister triple dog dare.
I triple dog dare you.
Schwartz created a slight breach of etiquette by skipping the triple dare and going right for the throat.
All right, all right. Come on, Karen. Well, go on, smart ass, and do it. I'm going.
Flick's spine stiffened, his lips curled in a defiant sneer. There was no going back now.
This is next.
course, then the teacher asks where he is, and of course, nobody knows. Yeah. All right. So I wanted to. I think it's obviously a funny clip. The whole movie is very much like that. It's like I say, it's an old movie, but it's a lot of people. It's kind of a cult classic, I guess. So his tongue stuck to the pole. I'm not really super interested in the details about why it stuck to the pole. I think we're okay with that. You know, the pole's colder than his tongue. So when he touches it, the water, the heat from the water on his tongue goes into the pole. And then since it's losing heat, the average kinetic energy is less, and the saliva basically freezes to the pole, basically is what's happening. But my question is this. If we were to take a wooden pole, right? You've all been out on a cold day, maybe not here in Muscat, but somewhere you've been somewhere that's cold, and you felt something that's metal, and you felt something that's wooden, and they've felt different, right? The metal generally feels colder than wood. If he were to lick a wooden pole, I've never heard anybody say, if you lick a wooden pole in the winter, then your tongue will stick, because it won't. Why is that? And I'm going to send you out in breakout rooms. I'm going to give you a minute. I want you to think about, why is wood different from a metal pole? Why would it stick in one scenario, not the other? Why does one feel colder than the other? All right. So here you go. Breakout rooms. And go. All right. Hey, Zaid, what'd you guys come up with?
We came up with that metals were better conductors of heat than like a wooden pole, but then we weren't sure what properties of metal led to that, but we weren't quite sure how to explain why metals were faster at conducting heat, or better. Yeah, so that's what we came up with.
All right, good. Anybody want to add anything to that? Thoughts? Yeah, Akrit.
I must preface this by saying that I was with Whitney, so I won the game. But he said specific heat capacity lends the steel to transfer heat faster than wood. Yeah.
All right. Anybody else? Okay. Awesome. Yeah. So those things are true. Yeah. The metal transfers the heat a little bit better. Well, significantly better. The reality is they're both at the same temperature, right? They're both sitting outside. they're both at thermal equilibrium with the surroundings, right? The 0th law of thermodynamics says that if they're in thermal equilibrium, if you let it sit there long enough, they're both going to be the same temperature. And so both the metal and the wood are the same temperature as everything else around them. The difference is the ability of the metal to transfer the heat. And that is because the same reason that makes metal a good conductor of electricity. It's the electrons, right? When we talk about transferring energy, we talked about the fact, and you guys all mentioned this, that when two things are in contact with each other, how is the heat actually getting from one to the other? It's because of the molecules, right? The individual molecules of the surface that are bouncing into each other and physically transferring transferring energy over there. Very good question, Isaac. We should try that. No, you should try that. I'll be an observer. I'll take notes. I'll time you. We got to make sure to do at least 3 trials, though. Make sure that we're being consistent. So I'll need 2 more volunteers that want to find out how long it takes for the wood. All right, we got Akrit. Well, all right, David, wonderful. As soon as it freezes here in Oman, then we'll run that experiment. Okay, so yeah, so it's the electrons, right, that are because the free electrons in the metal can move around. They're the things that make it easier to transfer energy 1 electron at a time over to the other side. All right, so that's the idea of the transference of energy. Now, there's 3 different ways that energy can be transferred from one place to another. Okay, one is like we talked about with the wood and the metal pole. That's what we call conduction. We also have convection. And last of all, radiation. Okay, how comfortable or how familiar are you guys with these 3 terms? I'm not sure. You may have done it in chemistry or something. Can you give me a thumbs up if you think you know everything to know about it? Maybe a thumb to the side if you're somewhat comfortable because you've heard of it before, and a thumbs down if you really have no idea what I'm talking about. All right, good. So it looks like at least most of you have some comfort level with these 3: conduction, convection, and radiation. So what we're going to do now is we're going to talk about each one of those. We're going to start with conduction. I'll give a little bit of a summary, and then I'll give you a break. Okay, I want you to have in your mind, yes, I am actually going to get a break very soon here. So we'll talk a little bit about conduction. We'll take a break. When we come back, we'll do some calculations with conduction, and then we'll move into the convection and the radiation after that. And hopefully we'll wrap all that up by the end of class today, so that next time we can move into the real thermodynamic stuff that is part of this unit. Okay, so conduction is when you have 2 objects that are in physical contact, neither one is moving. The energy is, that's what we talked about before, where the particles in those 2 objects are literally just banging into each other because of their vibrations or because of the free electrons and the metals, right? That those particles are just banging into each other, transferring energy through the Newtonian mechanics, through energy transfer, through momentum transfer, right? That's what's happening in conduction, okay? We do have a formula in our formula packet that deals with conduction. And it's important that you recognize that this is only for conduction. And my fat head's in the way. There you go. So Q over delta T is equal to KA delta T over L. Let's see if we can break it down. What do these things mean? And how would that affect heat transfer? Okay, so can we think about that? What could these 2 things mean, and how could that affect heat transfer? I'll give you a little bit more context. Most of the time, 99% of the time when we use this, you're going to have two objects right here, and you're going to have something in between that's acting kind of as the conduit, that's connecting from one to the other, that's allowing the heat to transfer from one place to the other. All right, because if two things are in contact, we assume that at the point of contact, the temperature is the same. Okay, and so what this is going to do is this is going to allow us kind of that conduit for that temperature gradient to take place as heat is moving from one to the other. And again, in most situations, we're going to be maintaining these at a specific temperature. Okay, we may get to the point where we talk about, well, how long would it take for that energy to transfer? But unfortunately, that requires some calculus. And so we probably won't even get to that unless we have a graph or something that allows us to do it graphically. All right. So what would each of these variables mean? What do you guys think?
I'm not on the equation sheet for sure, but L is thickness of the materials. I mean, no, the material in between. I don't know what L is the thickness of. Actually, that's what I was gonna ask, but.
Okay, so L is going to be, let's come back to L. Okay, when you say thickness, what do you mean, Akrit? Maybe you have it, you're just not saying it in the right way.
Would it be the distance in between the two objects that the conducting, like the green cylinder, the distance of that green cylinder? Is that L?
That is L. Yeah, that is L. What would the Q over delta T be, guys? This is going to help us understand why L is there and why T is there and why A is there. What does Q over delta T represent?
The rate of heat transfer.
Yeah. Q is the amount of heat, right? The amount of energy that's being transferred. That's what Q is. And of course, T is the amount of time it takes for that energy to transfer. In fact, sometimes they just label this as H. Now, H is not in your formula packet, but sometimes they do H, which is what we call the heat current. How much heat is flowing through, because we are, like I said, we're talking about it kind of as a conduit, how much heat is flowing through in a given amount of time. Okay, so that's what this heat current is. All right, but in your formula packet, it's shown as Q over delta T. All right, so L, Akrit said that L is the length between the two. Why does it make sense for L to be on the bottom of the fraction?
It makes sense. No, Isaac, go ahead.
Okay, if L is bigger, then you'd expect it to take more time for the heat to transfer.
Yeah, why would it take more time?
Because it has to move through more material.
It has to go through more material, so we expect the flow rate to be slower. It's kind of like when you guys studied resistance last year, right? Oh, wait, did you guys do resistance? Did you get to that? Maybe did some in the summer.
In the summer, yeah.
Yeah. Okay. I now remember that he said something about that. That's going to make our electronics unit very interesting later this year. But anyway, yes. So when you talk about resistance, what's making it more difficult for the heat to go from point A to point B? Well, if you have a larger distance, then remember it's all these collisions, all this bumping, and that is more difficult if there's a larger distance it has to travel over. Okay, so yeah, it makes sense for that length to be on the bottom. All right, what about these other things? I got a couple of things up here on the top. What could those things represent? I can't see everybody right now, unfortunately. I've changed his speaker so that the screen is bigger in the video.
Maybe like the area.
What's up, Sophia?
The area.
Area? Okay, what would area be?
A, like the area of the object.
Which object? Where am I looking at when you say area?
Maybe the area of the object that's transferring, or like that's like.
So are you saying like the surface area? Are you
No.
talking of?
Yeah, I'm not sure.
Ah, okay, you're close. It's definitely got to be something to do with this. What area would make it, because it's on the top, right? So when I increase area, it's going to increase my heat current. It's going to increase the flow rate. So what area here would allow the heat to travel faster?
I'm not too sure. Maybe like, I know they're not really in contact, but the area, if they were like the area of contact between the two. So like,
Yeah, this right here, right? That area right there is the area that's in contact with this guy. And assuming that it's the same area on the other side, then it would be, what do we call this area?
cross-sectional area.
Yeah, the cross-sectional area. You got it. We're going to say that that's the cross-sectional area, because that's the area. That's how much space. You can think of it as a pipe, right? You got a pipe of water. Are you going to get more water if you got a small pipe? Or are you going to get more water if you have a big pipe, right? A big pipe allows more water to flow through faster, just like this. A larger surface area, not surface area, cross-sectional area is going to allow your heat to travel from one to the other more quickly. That's exactly right. Awesome. What else?
Shabbat, I have a question about the
What's your
area.
question?
If you have a conical object that is connecting the two objects, a conical conductor, then would it be the smallest area
No.
or would it be the average area?
That's going to get significantly more complex, which thank goodness we don't have to worry about.
Okay, so everything that we will have will be equal area throughout the object.
Very good question, but one I'm not going to answer. It's going to take too long. All right. What's the T?
Temperature difference between the two objects.
Okay, temperature difference, right? Between object one and object two, and that should make sense. Larger temperature difference, larger gradient should mean a higher energy transfer, right? Same thing with pressure. You have a higher pressure difference, you get a larger force, right? So it connects, it makes sense, everything here. This is the temperature difference between your two objects there. Okay, the only thing that we haven't covered is this K. Okay, so the K has to cover everything else. We already said that different materials have different abilities to transfer heat. We said that metal has a much better ability because of its free electrons. Wood has less of an ability, okay? This is what we call the heat transfer coefficient. Okay, and the heat transfer coefficient depends on the material. You would have to either be given it or you'd be given all the other information and be asked to calculate it. This is something that you could do as an exploration, right? You could find the heat transfer coefficient of a specific material by using the surface area and the length and finding out how long it takes for the heat to transfer over, right? That's something that could feasibly be done as some type of exploration or investigation. Okay, so we've got all the pieces now. The one thing I do want to mention is that we do need to be careful with the length, okay, and that the length needs to be parallel to the heat transfer, okay, and I think that we kind of have that idea from our picture and from our discussion, but one thing that the textbooks and AP and everybody, they all say, make sure that when you use L, that you're talking about the length that is parallel to the heat transfer. Okay, so I just wanted to make sure to highlight that. We'll see that when we work some examples here in a couple of minutes. Okay. let's take a break. I think we need to take a break. I think we're at that point. Okay, take a break. We'll do a couple of examples afterwards. Okay, see you in about 3 minutes. Awesome. Okay, so yeah, I'd like to work a couple of problems now. All right, we're gonna do 3 different problems as examples, just so we have an idea of the types of things that we can run into. We'll start with an easy one and move on from there, and hopefully hit a couple of other concepts as we go. All right. So before I do that, I do want to mention sometimes the heat transfer coefficient, that K, is called the thermal conductivity. And so depending on your textbook or depending on the website, it may refer to that as thermal conductivity. And I believe that the OpenStax may actually refer to it as thermal conductivity. So if you see that, it's the same thing. Thermal conductivity and the heat transfer coefficient are the same. Okay, so yes, let's step over and work an example. All right, so this is an example. Yes, K. Yes, that is, okay, so it says in the equation packet as well. I couldn't remember what it said there. Perfect. So yes, this is the first example. This is example, I think, number 8 in your student packet. We've got a styrofoam ice box. The styrofoam ice box has ice and drinks inside, so it's keeping it at 0 degrees Celsius. Outside, it's a warm day, not uncomfortable, 30 degrees Celsius. It tells us that the surface area of the walls and the lid are 2.0 centimeters. As we do many times in our AP Physics courses, we're going to just assume that it's the same thickness and that it's just the same thing everywhere. We're not going to worry about the fact that we've got some corners over here that are actually going to make it longer on the outside than the inside. We're just going to assume the simple situation that doesn't actually exist, but it simplifies our problem. So we've got a wall thickness, so it tells us that the actual wall is 2 centimeters thick. And then, so surface area, wall thickness, temperature inside, temperature outside. What we want to find is the rate of heat transfer. How fast is energy going to be transferred from the outside to the inside? All right. Awesome. So what should we do?
Can we find the internal energy? Or wait, no, we need a thermal conductivity constant first, right?
Going to need a thermal conductivity constant. Yep.
I
That-
suggest we use the equation K equals 3/2 kVT.
Okay. Why is that?
If we figure out the kinetic energy, we can rearrange to solve for kV.
Okay. Is that KB the same K though?
I don't know. That's the only thing I could come up with, and I think it's wrong.
Yeah. What is that KB?
It was like NO over something. I forgot.
Boltzmann's
Yeah,
constant.
It's Boltzmann's constant, right? Yeah. So unfortunately, not the same K. Okay. I'll give you a hint. In all of these, I don't give a heat transfer coefficient. You have to go look it up. You got to look up the thermal
Oh, okay.
conductivity. Yeah, sorry. So we'll have to go look it up. Let's use our superior searching skills and see if we can styrofoam here.
At 20 degrees Celsius, It's a thermal conductivity of 0.022. I think that's watts per meter Kelvin.
Okay, awesome. Which sounds like it's in a good SI units for us there. I'll give you a further hint. Where all of the examples I'm going to use today are going to have thermal conductivities that we can get from OpenStax, chapter 14.5. So go ahead and open that up. OpenStax 14.5. We're actually going to use a couple of them. Just know that either they're going to be giving it to you or that's what you're solving for. They'll have to give you everything else. But for today, we'll go ahead and use this. There's a chart there. The problem is, I mean, part of this is I wanted to see when you look it up, you get lots of different values. Akrit, you mentioned a 0.22. I see in the chat that Isaac found a 0.033. Right, you're going to get different values if you look it up. That's because styrofoam can be made of different things. It can be slightly different. It works differently at different temperatures, right? Depending on how well the electrons and the molecules inside can move around. It depends on a whole lot of things. So we're just going to go ahead and go with what we have here in the text, the OpenStax. In here it says styrofoam is 0.010. And it gives basically the same units you mentioned, Akrit. It has joules per second, which is watts, times meters, times degrees C. Now, you mentioned, Akrit, before, you said that the one that you found was in Kelvin. The one in OpenStax is given in degrees Celsius. How does that work? I mean, they're different scales, right? How does it work to be able to use degrees Celsius if it's not an absolute scale? This is
Degrees Celsius and Kelvin have the same rate of change. And
that's right. That's right. And if we look at our equation here, which is Q over delta T equals K A delta T over L, it's always finding a temperature change. And so it's okay to use Celsius because, as Akrit mentioned, we're finding a difference between temperatures. We don't actually ever use an absolute temperature. Okay. Awesome. So we've got thermal conductivity. Isaac looked it up for us there, and I know a couple of other people did, but he typed it in the chat there. 0.010 is what OpenStax gives us, just so that we can be consistent. We'll all use the numbers from there. So that's our thermal conductivity. Because it's in SI units, then we don't need to worry too much about the units. What is my area going to be? What is the area that I'm going to use? What's the area through which the heat is being transferred?
Well, the surface area is 0.8 meters squared. But is that just one surface? I don't know.
No, that's the surface area of all of it. Yeah, we'll do easier this first time. So yeah, that's the surface area. That's all the surface areas. So that's always the surface area, as was mentioned earlier, is your cross sectional. That's perpendicular to the flow of the energy. And so that's going to be all of the surfaces of your box. The energy is going to go through those surfaces. Okay, so that area will be our 0.80 meters squared. I actually can't see myself right now. I don't know if I'm going outside of I am going outside a little bit. Okay, there we go. Okay, the temperature difference we have 30 degrees and 0 degrees. So the change in temperature is going to be 30. And then we're going to divide by the length, which the length is parallel to the heat transfer. So that is the width then of our box, which it gives us is 2 centimeters. We want to put it in meters. So 0.02. And that should allow us to get Q over delta T, which is the rate of heat transfer. Anybody have a number for that yet?
I have a question
Yeah.
about the change in temperature.
Okay.
So would it be the temperature, so T2 minus T1 for difference?
It is. It is. Really here, and it's up to you how you want to look at it, right? It really depends on what we're considering as our system and where we're starting. You probably could say that the outside is the initial and then the inside is the final, which means that you're going to be doing 0 minus 30 and you'll have a negative 30. The only thing that should ever do is change the sign, which is going to represent the direction of the heat transfer. And so in this situation, the heat transfer is going in, right? From the outside in. So I think you could do that. And if we're being under one convention, it would be a negative 30, and that's fine. I don't think that it matters too much as long as you recognize which direction the heat is transferring in.
Thank you.
I see some I got that's 2, but I didn't see the number yet. So I see 12 joules per second. Got a couple of people with that. All right. I'm realizing that once again, time has slipped away from me. Always seems to do that when I'm having fun. So I've got about 2 minutes left before the end of class. So I want to mention 2 ideas because I think that with practice that idea will come in pretty smoothly. So the last thing that I want to mention is that we will have questions similar to this, where we may have 2 different materials. Okay. We have 2 different materials that are in between causing the transfer of energy. Okay. Now, in those situations, what has to be true is that the heat transfer has to be the same. The rate of heat transfer, the H or the Q over delta T has to be the same for both of those materials. Okay, now that should make sense because if the heat transfer was faster for the steel than it was for the copper, then we'd have a buildup of energy right in the middle. Okay, now a buildup of energy means that it's going to be hotter. If it's hotter, that's then going to change the heat transfer through the copper, and it's going to make the copper go faster. Okay, so nature will automatically balance that out. Maybe not immediately, but once we're in that kind of equilibrium state where we have a constant flow from one to the other, nature will figure it out. Physics is amazing that way, is that physics will figure it out so that the heat transfer, the Q over delta T, is the same for both of those. Now, what that means is that the delta T, the temperature will be different across each one of those 2 things, right? It'll have to be different for the steel and for the copper. Whichever one has a lower thermal conductivity is going to have a higher temperature difference, right? If we're thinking about our equation here, if I want my heat capacity to be the same, because we see that the areas are the same, if my heat capacity here, the thermal conductivity is lower, then the temperature gradient across that specific material is going to have to be bigger. Okay, so that's one thing that we want to take note of. Just that if I have 2 materials together transferring from one end to the other, that the heat transfer rate has to be the same for both of them, the heat current. Okay, if they're next to each other, if they're in parallel, we call that parallel. Like I say, I don't know if you got to that in electricity or not. If they're in parallel, this is what we call series, one running into the other, and it has to go through both of them. The other one is if they're in parallel, one on top of the other but not touching, then what needs to happen is that the temperature gradient has to be the same. The heat flow doesn't have to be the same because the lengths could be different, the areas could be different, everything else could be different. What has to be the same is the change in temperature from one side to the other. All right. Okay. Any questions? Time is up. Okie doke. That's it for today. We'll pick up where we left off next time.
See you,
Thanks,
Mr.
everybody.
Bywater. Have a good one.
I had a question about the homework. I was confused about the partner chat number 6.
I just have to grab it. I don't have it in front of me. Okay. Partner chat number 6. Okay. Yep.
I just didn't know how to do it.
Okay. So what does the capital M represent?
The molar mass?
Yeah. So what is that? What is molar mass?
Grams per mole.
Okay. So it's the mass of a whole mole, right? It's telling us that the mu is the mass of one molecule. Okay. Which means if M is the mass of a whole mole, how do I get the mass of one molecule?
You divide by how many molecules in a mole?
That's right, which is
Avogadro's number.
number. Yeah, that's exactly right. And so therefore, you can substitute, you can move the NO over, and we can say that molar mass equals the mass of one molecule times NO, Avogadro's number, Steve, whatever it is. No, sorry, that's not Avogadro's number, is it? That's
Yeah.
R. Yes. So so now you should just be able to substitute that for the M. And then somewhere in your notes, it should say how KB connects to R and Avogadro's number. So you should
Oh,
be able to
okay.
use that. It's in the ideal gas law as well. You can see how it's kind of been changed.
Okay. Thank you.
That's it. I also saw your email. I'll respond to it soon. I've just
Okay.
been, I was up until like 2 grading last night, so I didn't have time to process it yet. But yes, I'll get back to you on that.
Okay. Thank you. Have a nice day.
You too. Hey, Whitney, what's up, eh?
It's about whether, so I have a question for the things like on the board. So when it's connected with two materials, you still use that equation, right? But what has changed?
Well,
Is
you
there-
have 2 different materials, right?
Yeah.
And so what you'll need to do is, I mean, it'll depend on the question. It depends on what it's asking for. Chances are you're going to have 2 different variables, right? You're going to have one variable, which is the rate of heat transfer, right? But you can write 2 different equations, one for the steel and one for the copper. But then you're going to have another variable because we don't know what the temperature is there in the middle,
Yeah.
right? You'll have the lengths, you've got the cross-sectional area, you'll have the thermal conductivity, which you can get from, you know, your table in OpenStax, but you don't have the temperature here, and you don't know the heat transfer. And so you'll have 2 equations with 2 variables, meaning that you can solve for both at the same time.
Okay. Got it. All right. Thank you.
Good question.
Have a nice day.
You too.